part two. Man, that took a long time. Part two. As you look out at the field of springs, you feel like there are way more springs than the condition records list. When you examine the records, you discover that they were actually folded up this whole time. To unfold the records on each row, replace the list of spring conditions with 5 copies of itself separated by question mark, and replace the list of contiguous groups of damaged springs with 5 copies of itself separated by comma. So this row would become, the first line of the above example would become, the above example after unfolding the number of possible arrangements for some rows is now larger. Unfolding, adding all of the possible arrangements counts together produces what is the new sum of possible arrangements. Yeah, so that becomes a lot more complicated. But I think we're pretty performant, or at least we're fast enough with the method that I'm using. I think I'm just going to go ahead and unfold them. And yeah, part 2, we'll call it that. And so I could just do that here. Or I could do a separate one. Oh, and then there was one last part here, which was, so this becomes, one, two, three, four, five. I think I misunderstood. I see what I did wrong. This needs to be, So now part 2. So I just had to unfold these properly. So now part 2. Let's run it. Probably be a little slow, but I think it'll finish. Let's get rid of this because it's going to be a lot of output. It's part 1. I wonder if there's like a mathematical way to compute this. Probably not so directly. I mean, you know that the number is going to be at least 5 times the size. I suppose it's a repeated pattern. So once you determine it for one set, you could repeat that for the other sets. That'd probably be more optimal. Do some sort of like pattern indexing. What do we have? Like what? 1,000 of these? So if we want to know like where we're at, we could do something like what's the third one in this input? That's a lot of question marks. So we can remember different patterns based on the input. So if I create a cache, we'll call it cache, and we'll say it's of map string, and yeah, it'll be string, and then it'll be some count, which will be the count that we know, and the input will have to be whatever our key is, and then the count. Anytime we get here, we'll catalog our cache sub s, whatever our s is, equal our total count. But this isn't just s. But it also needs to be our record sub our records, and our key just needs to be that, I think. And then I think we can say if let's move this somewhere else. Let's move this up. I'm going to create a key up here so I can do it once and just nope. All right, let's see how that fares. Okay, so by caching these values, our tests still pass. Let's see if we can cancel this and rerun. Okay, well, that was much faster. There we go. Awesome. Got day 2. All right, let me recap. That was a long process. But to kind of recap, first, part 1, we simply created a recursive function that after parsing our data, we're trying to get the number of arrangements just by a pure count. And we're passing in our spring and then what our current records say they are. The way we accomplish that is by looking for key values and moving forward, and then as we would find one segment of a springs, we would then segment off and ask for the next segment to be considered removing the first record. That's the approach. And as you see here for us, this was a lot of calculations, and I'm not sure if everybody got the question marks, but that definitely took a really long time to calculate. And interestingly enough, there's even larger calculations after that. So we didn't even get past part 3, and we ended up all these other issues. So in order to solve for that, just based on the amount of input that we had to cache. And so the idea there behind the cache is that we were going to, every time we calculated a pattern, and this was a pattern based on input and patterns, we were going to cache that in a map. And then if that pattern is seen again in the future, instead of having to recalculate that pattern, we already know the answer for that pattern. So, in the case of the all question marks, well, the first time through, we calculated question mark 1. And here we can go back to our diagram here, and I'll pull. So how this caching mechanism works, if we use this as an example here, the first time through, if we've got like 1, 1, 3, like we have over here, we start here on 1. And because this is a valid match and this can become a period, right? We send this string to the next process. That process then looks at, I think my pen might be dead. Well, that's sad. Okay. Well, we'll do it here. So we then look here and here on the first pass, or that's the second block, and then that gives us this final block here to look at. So at each of these steps, we're caching the entire string. So we know now at this point, we're going to segment this off, and then what we end up with is us then processing this whole string for the different options for the number 3. And what we do is when we put in our cache, we put the fact that we are looking for this number of question marks and the number 3. So you end up in our cache with something that looks like this. Something like that. Maybe not exactly right. And equal, the value to that is equal whatever it is. How many ever times it can make 3 with just a bunch of question marks. That's what's in the cache. I don't think it's 10, but just as an example. So then the next time we come in and we start with indexing here, and then here, and then here, when we get to here, it already knows what that looks like for a 3. And not to mention, we also cached the other iterations of the subcomp parts all the way down so that it was able to do a lookup and provide that very quickly. So that's why the cache had such a huge impact on performance here, and why that it was able to help us solve this problem in a reasonable amount of time. And really all we had to do was just add a couple of things here. I think probably what I would change in the future is not initializing cache in the global space and somehow injecting that, but this is fine. So that's pretty much the solution. But as always, over and out.